Hi, I'm Brian Vanderwijn from the CISL Consulting Services Group. I'm going to present a tutorial today on job scheduling with PBS Pro. So PBS Pro provides resources on our systems here at NCAR beyond the login nodes. This includes resources like the HPC compute nodes on Cheyenne, the high throughput computing, high memory visualization, and GPGPU nodes on Casper. The Jupyter Hub jobs on both Cheyenne and Casper use PBS Pro jobs to give access to resources. So one thing to know about PBS Pro on these systems is that Cheyenne and Casper each have their own unique PBS servers, and each one manages the job scheduling on each system. However, these servers are peers, and what that means is that they can recognize each other. So if you're familiar with PBS scheduling on our systems over the past few years, the big new capability is that you can now submit jobs to either system from any location on Cheyenne and Casper, and you can create job dependencies between them. So this really enables a new level of complexity, I would say, on some of the job workflows that people can do. And you can really target your jobs to go at the particular go to the particular system that it's best intended for. So, one question that I think implicitly comes up, especially for new users who get access to our systems, is, why shouldn't I just run my script on the login node? I sign in, it seems like my usual workstation environment seems pretty capable, so why not just go ahead and do that? The important thing to remember is that the login node shared resource, and as a result we expect and in fact we enforce that there is fair usage of both the CPU cores as well as the memory, the RAM, on those login nodes. And as a result, your login session might be terminated if you run resource-intensive applications on those nodes. So it's important to use the login nodes for specific purposes, and some of the ones that we outline are things like script editing, file movement around the different file systems that you have access to, and simple compiles of programs, so compiles that use 8 or less make jobs or threads. That wouldn't include large model compiles. Those still are best to run on some of the compute nodes via PBS. And as a result, we're talking about running all of these PBS jobs, so you obviously need a place to run them from, and that's obviously the login nodes, or sometimes they're called the front-end nodes, because they give access to the back-end resources via the scheduler. So, the first thing that we might talk about is what constitutes a PBS compute job, so the anatomy of a PBS compute job. Basically, a PBS job, just like any HPC job scheduler, it provides you with a pool of requested resources with which you can run a batch script of commands, or you can gain an interactive shell session that you can run commands through a usual terminal interface, or perhaps, say, a Jupyter Hub job, which will give you a web interface. In PBS, these resources are defined either at the job level or what PBS refers to as the chunk level, and I'll describe the chunk level first. So what a chunk is it's just a collection of resources of a defined type, making up a particular portion of the pool of resources in your job. Oftentimes these are synonymous with nodes, but you can have multiple chunks on a single node in PBS. So while they're related concepts, there are distinctions between the two. And for your job, you do set some resources at the job level. So these resources would apply to all of the chunks that are in the allocated pool that's assigned to the job. And here's a sampling of the resources that fall under both types on our systems. So at the chunk level, you would have things like NCPUs, this would be the number of CPU cores you have access to, MPI procs, which is MPI processes or tasks, OMP threads, so that'd be OpenMP threads, the mem, which would define the amount of memory that's available to your job, and then on Casper, you'd have NGPUs, which would give you access to a number of GPUs. At a chunk level, you can also specify CPU type. So on Cheyenne, all of the nodes are Intel Broadwell cores. But on Casper, we have a bit more heterogeneous of an environment, so they're currently Skylake and Cascade Lake Intel CPUs, and there may be more types moving forward. And at the job level, you would define the wall time, so the amount of time that the job is allowed to run, the maximum amount of time. This place category, this is something you probably won't play with too much, but you can tell PBS how you want it to place the chunks. So for example, if you had chunks that were smaller than the size of a node, you could tell it to pack all of those chunks on as few nodes as possible, or you could tell it to spread those chunks across as many nodes as possible. And we have same default set for that, but there are certain use cases where you might want to play with that. And then on the at the job level, you can specify the GPU type, as we have 2 types of GPUs on Casper. So, if you want to interact with PBS, there's a set of commands, terminal commands that you would want to remember. So there are broadly 4 job management commands that are typically used. There's some more, but the ones that you'll interact with regularly would be qsub. This is the main way in PBS to submit jobs, and we expect that's the main way to submit batch jobs. You can submit interactive jobs with qsub as well. But typically you use it for batch jobs. The reason for that is that we also have 2 helper scripts, which sort of take some of the syntax, they simplify the syntax for submitting interactive resource requests. And you would use qinteractive to submit interactive jobs to Cheyenne, and you'd do exec Casper to submit to Casper. If you have a job either pending or running that you would like to terminate, you can run qdel on the job ID, and that will cancel or kill a pending or running job. And so that's managing your jobs. In terms of querying available information, the 2 main commands there would be qstat, which will give you information about recent pending, running, or finished jobs. Once a finished job is older than, say, a day or 2, that information won't be available via qstat anymore. It's a rather short query period on those logs. But we do have a qhist command as well, which will give you historical information about finished jobs only. So if you have a job from months ago even that you want to query, you're able to do that using the qhist command. And we'll talk more about most of these commands moving forward in the coming slides. So let's start with a batch job. If you want to submit a batch job on Cheyenne, you'd submit it using the qsub command, as we mentioned, and you'd have a batch script, which is just a text file that has PBS directives, which give information to PBS about the characteristics, the metadata of the job, and then a series of shell commands that are either run by, say, bash or C shell, or you can even create Python job scripts, and those will run once the job starts, once it has resources allocated to it. So on the right here, you can see what, this is a sample PBS job. Here it's a bash script. These lines are all of our directives, so we're assigning things like a project code to charge to. We have a name for the job. We want to do some operations with our logs. Here's the queue, so we're going to submit to a particular queue, and we'll talk more about queues moving in a little bit. Here is an example of a job level resource, the wall time, and here's an example of defining our chunks. So we're asking for a single chunk, and that chunk has 8 CPUs, 2 MPI processes, and 4 OpenMP threads. And it's important to keep some of these in mind. There's some implications for the way these are defined, but as you can see here, we're running a hybrid OpenMP MPI job. So we want to have some sort of split of those resources that makes sense for our application. Once we get past these directives, then we actually have our job commands, and these are all, again, these are bash commands. So the first thing that we want to do is we want to initialize the job environment. So we'll set things like the temporary directory for temporary files. You want to direct this generally to your scratch space. If you leave this blank, it will, if you leave this undefined, it'll try to, your applications will generally try to write temporary files to the limited temp space on the compute node. It's very small, so that can be a source of job failures. So we recommend that you define this as your place in your scratch. You want to make sure that that place exists, of course. And then after that, do things like define your module environment. This is something that you could just use the default modules. They'll generally get loaded at the start of a job. You could define a default module set that's custom to you, but we recommend generally setting these in the batch script itself. That's nice for reproducibility, it's nice for portability, and it's also nice if you want to share your script to a colleague, for example. And in that case, you would run, they would be able to run this and have access to the same modules and not need some information that's, say, in your startup files or in your default module configuration. So at that point, once the environment's set up, then we can simply run our application here. So it's an MPI-enabled application, so we use the MPI launcher. We're also going to use this onPlace utility, which, if you're familiar with the MPT MPI library, this helps pin processes when you have these hybrid applications of OpenMP and MPI, and then we run our application. One thing I like to do at the end of all my jobs is to run qstat, use this -f option. We'll talk about later, but that basically gives a full query of the job. And then I specify the job ID, which is given by this variable. And that's nice because then I have this full output stored in my job logs. So it's easy for me to dig into those logs days later and still get all of this information. I don't have to query it from anywhere. And in fact, the full output here you can't query after a day or two. So just some notes about all of this. Any of these PBS directives that are defined in the job script here can be overridden by qsub arguments. So, here I run qsub in the job script. I could, in fact, have qsub-q and then a different q, for example, and that would override the regular setting in the job script. So the command line arguments take precedence. The batch job will start in a clean environment. So for a while, it was configured on Cheyenne that your login node settings would be imported or inherited into the batch job. This isn't the case any longer. Now you'll get basically a clean environment, but it will source your .profile and your .tcshrc file depending on what shell you're using as in the command here. So that's something to be aware of. The job-specific environment settings, as we mentioned, should go in the script. And then the other thing to know is that once you submit the job, it will wait in a specified queue until the resources are available. So that's the whole point of submitting to the regular queue here, for example. Just a little bit about interactive jobs. So, interactive jobs, we mentioned those commands before. Basically what they do is that they're going to start a shell on a compute node. It's basically very similar to your login session. It's just on a compute node with access to more resources and oftentimes exclusive resources. So the default settings, if you run one of these commands, it'll give you 1 CPU core using your native shell. And it will give you 1 hour of wall time on the share queue by default on Cheyenne, and 6 hours of wall time and 10 gigabytes of memory on Casper if you run exec Casper. We'll talk a little bit more about queues moving forward, but as you can guess, the share queue is, you end up on a node that's shared with other users. On Casper, memory is a bit more important because memory is reserved, which we'll talk a little bit about too. So it's important to note that you can override these defaults when you use these commands. So custom PBS settings can be passed either to either command, and it'll accept the qsub arguments. So everything that was a directive in the prior batch script can be specified there. We also provide short form settings, which are listed on the right. These are arguments that both QInteractive and exec Casper will accept. And this is just a bit shorter for some of the syntax. So for example, if I wanted to ask for a single MPI task, or specify the MPI tasks, I could do it using that short form command. And here's some examples. So here we have 2 calls to exec Casper, and these do the same exact thing. So the first one, we have exec Casper, we give it a project code, and then we use the PBS syntax to say select one chunk with 1 CPU and 20 gigabytes of memory instead of the default 10. I could also run exec Casper, give it the project code, and then just say --mem equals 20 gigabytes. And every other thing that would be specified, like the single CPU and the single chunk, will be left default. The nice thing with these commands is that they will show you when you submit the qsub output that you would get, or the qsub command that you would run to get the equivalent request. So I'll show that to you right now. In this terminal, you can see we're on a Cheyenne login node, Cheyenne 1. And if I wanted to get access to, say, a Cheyenne shared job, I could just run q interactive. I can do -a, give it a project code, and then let's say n threads, and let's use 4 threads. So here we go, it's submitting the interactive job to PBS, and it's going to tell me that it's running qsub-i, giving it a queue, the share queue, the project, it's giving me the default hour of all time, and here we go, OMP threads equals 4. So there we go, and we can exit out of that interactive job there. So, you know, that's really, it's pretty simple to use those commands. So let's talk a little bit about queues. We've alluded to them thus far. So queues may assign priority or route to a shared node. That's basically the two purposes of queues on each of the systems. So on Cheyenne, you might assign your job a priority and a charge factor, which are inversely proportional. And what I mean by that is when you have a priority category, generally the higher the priority of the job in the queue, the shorter the wait time. But we balance that, I suppose, by having a charge factor that's higher. So most jobs will probably get submitted into the regular queue, which is the default. But if you wanted to potentially reduce your wait time and charge a little bit more in terms of core hours to your project, you could submit to premium and try to get that job to run sooner. Or if you want to save a little bit, but perhaps you don't care how long you wait, you could submit to economy, and jobs in the economy queue will have a lower priority than jobs in the other two queues. So this gives you a little bit of control. And the important thing to know about these three, or one important thing to know about these three queues, is that they all give you exclusive use of a node. So no matter what amount of resources you request on each chunk will take up a full exclusive node. And that is, you know, that's just because the assumption on these queues is that you're going to run one or more full nodes as part of your job. Cheyenne does have that share queue as well. This is for smaller jobs, so less than or equal to 18 tasks, or half the size of a Cheyenne node. And it's on a shared node, so the cores in the memory are not reserved to you. They're accessible to anybody. That's something to be aware of on the Cheyenne share queue. Now Casper works a little bit differently. So on Casper, we actually only have one submission queue, though that's not technically true anymore, and I'll mention that in a little bit. But there's one main submission queue, which is the Casper queue. This is what's called a routing queue. So you submit to this queue, but then your job actually gets routed to one of a number of execution queues where the job will wait, gain priority, and eventually run once it has access to resources. And this is important to know purely for the fact that when you query that job after submitting it, you'll probably see one of these 4 queues. You won't see Casper. So if you say, okay, I submitted my job to Casper, but it says it's in the viz queue, you know, what's up with that? It's because of that routing that happened there. And you can see some of these categories that we'll route for. So if you ask for, say, a few CPUs, a relatively low amount of memory, and no GPUs, your job will probably go in high throughput, the HTC queue. If it needs a very large amount of memory, then it will go into large mem, and there is a restriction on number of jobs that can be in this queue. If you need access to a GP100, a Quadro GP100 GPU, it'll go into viz if you request that, and that would be for, let's say, if you're doing some rendering tasks, you're, say, running Vapor or something like that. And then there's the GPGPU queue, which will give you access to the more powerful, in terms of compute, V100 GPUs from NVIDIA. These are really used for like machine learning and also CFD codes that are GPU offload enabled. We also have on Casper this GPU dev queue, and this can be directly submitted to, but your jobs will run in this queue as well. So this will give you access to a very short job, so it's 30 minutes or less, and a very limited number of GPUs. There are 2 nodes that are in this queue, so it's a total of 8 GPUs. So we limit it pretty heavily in terms of what you can request. But the idea here is that you might be doing some iterative development cycles. You don't need a lot of resources, but you need them quickly because you want to run something fast, debug it, and then try it again. In which case waiting in this queue during business hours might not be ideal. So we have this queue which is open during business hours on Monday through Friday, and you can submit to that and generally get a very quick turnaround time on getting access to some V100s. So, some things to note in terms of tailoring your job. So on Casper, again, we have this routing structure. So the queues are really set up to handle things based on your resource requests, those chunk level resources and those job level resources. So all of the requested resources on the nodes on Casper are exclusive to the job that's occupying them. This is different from Cheyenne. So on Cheyenne, if you ask for an exclusive job, you get access to the full node, so it's exclusive in that sense. But if you're on a shared job, the resources are basically, it's a bit Wild Westy there. If I want to use, all 18 of the cores, I can do that. If I want to use a lot of the memory, I can. So you generally want to be a good citizen on the share queue on Cheyenne. But on Casper, we use Linux control groups, and what that allows us to do is actually lock down the resources that you request on those shared nodes to you only, to your job only, with one caveat being the GP100 GPUs, which are still shared. So, if I were to ask for, say, 30 gigabytes of memory, then I have access to all of that memory. That's great. It keeps me from stepping on other people, and it keeps them from stepping on me. But, be aware that it's a bit more important to specify a somewhat accurate resource request on Casper, because if I ask for most of the memory on the node and I only end up using like 10 gigabytes, then I'm really not being a good citizen to my fellow users, because that node is essentially now bogged down from my job, even though it doesn't need to be. So if you need access to a GPU on Casper, you have to specify an NGPUs amount in your PBS select statement. If you neglect to specify this, you won't get a GPU in your job. And while you don't explicitly have to set GPU type if you set NGPUs, we do recommend that you set both of them if you're doing a GPU request, because then that removes any sort of ambiguity that the scheduler might have in terms of whether you want a GP100 GPU or a V100 GPU. Generally have very different purposes. Another thing to note, you should always specify a per chunk memory request on Casper jobs, so that mem equals flag. This is important. If you don't ask for it, you'll get the default amount, which is 10 gigabytes. And if you exceed the amount that is requested, whether it's default or explicitly requested, your program will end up basically spilling into a swap space, this NVMe swap space. And that's good because it doesn't, it's better than failing, I should say. The job won't just crash, but it's going to run much slower. So you generally want to avoid spilling into that swap space if you can. Best just to try to request the amount of memory that you think you need and iterate over time based on the amount of memory that you find that you do use. And one last thing to note, if you don't specify the OMP threads flag, then the variable OMP num threads will be assigned to the NCPUs amount, because that's a resource that you always have to request. This can trip people up. Let's say I requested NCPUs 36, MPI prox equals 36, and I'm running an MPI program, but that MPI program is also OpenMP aware. What I'll actually probably get is 36 threads, each running on each of the 36 MPI processes. So I'll get 36 times 36 threads on a single node, which is not what I want, because there are 36 physical CPUs, and you're going to get a lot of context switching, and the program's going to run very slowly. So if there's any doubt, generally we recommend setting OMP threads. If you don't want to use OpenMP threads, just set it to 1. You can also export or set env the OMP num threads variable in your job script, and that'll override it. But if you actually want to use the value that's specified in the select statement, you should specify it using the OMP threads flag. So we talked about quite a bit about submitting jobs. We oftentimes get a question, why aren't my jobs running? Or we'll get it when there's any sort of concern. There's a number of potential reasons. One would be queue limits. So there are wall clock limits on both systems. It's 12 hours on Cheyenne jobs. It's 24 hours for most Casper jobs. There are GPU limits as well. For, let's say, for the GPU queue, you can have a maximum of 32 of the V100s in a single job. So, for the wall clock, if you ask for 13 hours on Cheyenne, it'll reject the job right at submission time. It'll say, I can't satisfy this. But the way PBS works is that for resources, for chunk level resources in particular, it will generally allow you to ask for more than is available. And it will do that under the assumption that, hey, maybe someday we're going to add more of those and the job will be able to run. This generally isn't the case. We're not adding resources that frequently, and we announce it very broadly when we do. It's not a very dynamic resource pool at our site like perhaps it would be at some other sites. So you want to be mindful of the resource limits, and those are documented on our web documentation. Another example of that would be the core limits. So the 18 CPU limit on share queue. You don't want to ask for more than that because the job will never be able to run. It'll get stuck in the queue. Another reason why that might happen would be resource conflicts. So if you have a job that requests a GPU type of GP100 and a CPU type of Cascade Lake, this job can never run. And that's because we have no nodes that satisfy both of those requirements. And unfortunately, PBS doesn't know that at submission time, so it'll allow you to submit it, but that job will just sit in the queue and not be able to run. For FYI, all of our GP100 nodes run Skylake processors, so you would need to specify that if you wanted to restrict that like that. And again, all the node types are defined on our web documentation, so you can double check it there. Another reason that's not necessarily a deal breaker, but can make your wait in the queue a long time, would be if you have very large requests. So if you're asking for a large amount of a very popular resource, for example, the V100 GPUs, this will result in difficult to place jobs. So it may be a valid job, but PBS has a hard time placing it because of that large request. And sort of along the same lines, if there's heavy usage either by other users or by yourself, you're going to have a hard time getting through the queue. When I say by yourself, because there is a history factor. This is part of the fair share calculation. And if you've submitted a lot of jobs recently, your fair share score might be lower than the priority fair share score of somebody who hasn't run any jobs recently. And as a result, their jobs will have a higher priority, and it seems like they'll run sooner. But it's actually because they weren't using the queue at all over the past month, and you were using it heavily. So we're trying to make sure everybody maintains their fair share. However, at one instant in time, it can seem a bit frustrating. So in general, just before you suspect a system issue, consider those conditions that we've outlined above and inspect the job using the qstat command to make sure it's valid. Just one last note, in terms of interacting with PBS as a Jupyter Hub user, there's a couple of things to think about here. So Jupyter Hub provides you with a web-based compute environment for running notebooks and terminal sessions on the NCAR systems. If most people these days are familiar with Jupyter, it's a really nice web API or web interface. But on the behind the scenes, basically what's happening is PBS jobs, for the most part, are being spawned, and your Jupyter session is running inside of them. So certainly for all of the batch servers that you can create in Jupyter Hub, these spawn PBS jobs. These Jupyter Hub jobs use core hour resources, so be mindful about stopping your servers when the work is completed. And one interesting thing to note here is that the Casper login sessions, the servers, they also spawn a PBS job too. This is done to maintain system stability. So it's sort of, it's a login session, but it's not. So please limit yourself to a single Casper login server at any time. And the above point applies there, that core hour resources are used for those sessions as well. Though on Casper, you're basically charged for the amount of CPU time you're using. So an idle session is using very little in terms of core hours. So I just want to show you real briefly, what this looks like. If I go to jupyterhub.hpc.ucar.edu, I get to this screen. Generally, most users are going to use our production instance here, and you will need to sign in and use your CIT password. Let's see, and you'll get an authentication. So there we go. It looks like I already have a server running, so I can see in this front screen here, it'll show you sort of a default server that you might or might not have running. We'll stop it just so we can show something, and then you can have up to 4 additional servers that are named in here as well. But again, try to use those for batch servers, not login servers. Generally, you'd only need 1 login server because it's a tabbed interface, and you can run a lot of stuff in a single server. So if I was going to start a new one, I would see these options for a Casper login, Casper batch, Cheyenne login, or Cheyenne batch. The batch jobs would be used again because you have access to more resources. So let's say I do a Casper PBS batch. So it would ask me for all the same things. So I would put in my project code, and then I'm just going to use the defaults for everything. Notice it'll default you to no GPUs, but otherwise, maybe I'll make sure I get 10 gigabytes of memory here. But otherwise, I'm pretty happy with that. It's going to give me a 2-hour job. I'll launch this server, and basically, right now that that job is waiting in the queue. Looks like it's already started. The cluster job has started. And once the server has loaded, basically, then I get dumped in here into the splash screen in Jupyter Lab in the web interface. So now I'm running in a PBS batch job. And I could do things like run Dask servers. I'm not going to run this right now, but you can use Dask to spawn up a PBS cluster, is what cluster object they call it, and this will basically submit more PBS jobs in the form of workers. So there's a lot of different ways to submit jobs here, and in fact, if I go back to the launcher, Jupyter Hub also lets you start terminals. So in here, I could run qstat-u user. This will just show me my jobs. And here we go. I can see that I've got, in fact, 2 Jupyter Hub sessions running here. I've got that login session, which is still terminating. And then I've got the batch session that I just started with 10 gigabytes of memory and 2 hours of wall time. So it's, it's visible as a PBS job here, even though it's a Jupyter Hub session. And again, when we're done with these things, we want to shut them down. So I can go to File, Hub Control Panel. This will bring up a new window. I can close the server window, and then I can click Stop My Server here, and that will stop the PBS job. So I won't be accumulating more core hours. So one word about peer submission and queue names. If you submit a job to Casper and from a Cheyenne login node or vice versa, you have to append the server name, the PBS server name, to the queue. So if you are going to submit to one system from the other frequently, then you might consider appending the server name all the time in your batch scripts. And what this looks like, so let's say I wanted to submit to the regular queue on Cheyenne from a Cheyenne node. I could just use regular. But if I wanted to submit to a Casper node, I would need to specify this, this string here, which is the Cheyenne PBS server's name. It's a bit clunky, but again, if you're putting it in batch scripts, it's pretty easy to reference that. For Casper, I could submit to the Casper queue from a Casper node, but if I'm on a Cheyenne node, I have to do Casper at Casper-PBS. One nice thing is that Q Interactive and exec Casper will handle this for you, regardless of what queue you specify. So if I ran Q Interactive and from Casper, for example, and I asked for the economy queue, it would append this server string at the end of it for me. I wouldn't have to put that in there, although it'd be fine if I did. So now that we've talked about peer scheduling a little bit, one really nice capability that's enabled by that is specifying dependencies between jobs, which can be done now across servers. So you can have dependencies that are purely on one system, or you can have dependencies across the servers. In PBS, it's very similar to other job schedulers, so I can create a dependency using this either command line argument or directive. Generally, you would do this as a command line argument because you would need to have access to the job ID number. But I can do -w depend equals and then the condition and then the job ID. So basically the jobs are held, they're in a held status until the dependency is satisfied, this condition is satisfied. And then once the dependency is satisfied, then the jobs are pending. So they might not run right away. You might still have to wait in the queue for resources to become available. Some of the conditions that we would care about, you'd have after any, after okay, after not okay. These are all defined right here. The one that's most common, I would say, would be the after okay, which is all of the jobs that you list in this condition have succeeded. So just a submission example here, let's say I had 2 ensemble CFD jobs that I wanted to run in Cheyenne. So this is, in a bash shell, so I'm using bash syntax. But basically I do a qsub -q regular, my Cheyenne job, my 2 ensemble jobs, and I store those job IDs that get output into variables, into shell variables. And then again, still from Cheyenne's login node, I can submit a post-processing job to Casper. And since I'm on Cheyenne, I need to do Casper at casper-pbs. And I give it this dependency. And I say, after those ensemble members have succeeded, if they have succeeded, there's the 2 job IDs, then run this post-processing script. But it will only happen if those original 2 jobs, if they finish with a exit code that is 0. So that's how, generally programs will indicate that they have successfully completed. And that's important to just keep in mind, because in your batch script, you'll want the final command that runs to report that error code that is either 0 for success or non-zero for failure. So generally you wouldn't want to have lines after that do other things, because it might muddy what the actual exit code from your application was. Okay, so we've talked a lot about submission. Let's talk a little bit about querying. So I can query active and recent jobs using qstat, and qstat is now peer-enabled, so it provides information on pending, running, held, and recently finished jobs on either server from anywhere on the systems. On Cheyenne and Casper, we do cache the output of qstat with a 10-second refresh rate, and this is done to help improve PBS performance, because if people run a lot of qstat commands frequently, it can slow down the server, which also affects running jobs and pending jobs. So we do cache it, but it updates very frequently, so it shouldn't generally put any impositions on workflows. And there's many different forms of qstat, many different options. Some of the ones I'll highlight here: you can show a single job if you give the job ID. You can show all of the jobs in a queue if you give the queue name. Again, I showed this before, you can list all of your jobs or somebody else's jobs if they specify their username. And I can get the long form output detailed info on a job if I do qstat-f and then the job ID. There is also the -x, which will include recent history. So again, this is about a day or 2 of finished jobs. We would recommend that you don't use the -f and the -x commands together too frequently, because this is hard on the scheduler. But all the other combinations should be okay. So here are just some examples. If I run qstat-u-w user, the -w I didn't put in here, but that's just a wider output, so I use that more in my terminal real estate if I have a wide terminal. I can show all of the historical and, well, all of the recent history, and as well as the current jobs in the Casper queue using -x. Now note here, I'm doing it from a Cheyenne login node, so again, I would do Casper at casper-pbs. One thing that we've added to qstat is that in addition to using the full server name, you can give the system name as well. So these 3 all do the same thing. If I'm on a Cheyenne login node, I can run qstat on this job ID, 1, 2, 3, 4, 5. Or from Casper, I can query this Cheyenne job by doing 1, 2, 3, 4, 5 dot and then the server name, or 1, 2, 3, 4, 5 dot and the system name. And you should note with queues, the server is separated from the queue name with an @ whereas with jobs it's separated with a dot. That's just something to be aware of in terms of syntax. Now, again, in terms of getting historical records, you can use the qhist command. So this is something that we provide by default. Qhist will give you all of the jobs from the current day, all the finished jobs. But there are plenty of arguments to change the time period and filter jobs by various criteria. So I could say, look through the past 5 days of records and give me all of my jobs. Or I could say, look from a start and end period given by dates, and look for a particular job ID during that period. But one thing to note about qhist, unlike qstat, it will only show you the jobs from the native PBS server. So if I'm on Cheyenne, it's going to show me Cheyenne jobs. If I'm on Casper, it'll show me Casper jobs. But really the nice thing about qhist is it can show you all this historical information. And a couple fields that are really nice here is that it can quickly query CPU and memory usage of past jobs. So here's an example of that. Let's say I run qhist, show all of my jobs, and I'm looking way back here, just to show that, the record goes way back. This is on Casper, so I'm looking at my Casper PBS jobs from basically once we switched from Slurm to PBS back in March of 2021, over basically a 5-day period here. And I want to sort all of these jobs by memory. And I'll look at the top 5. So I can see that this one job here is using, quite a bit more memory than the others. I'm kind of interested in that. So I look at this job ID and then I say, okay, well, this is from, 2021-03-23. So I can specify that as the period that I care about. Notice I can do a single day as well as a range. Specify the job ID and give me the long form output, which will show me more information here than I get from this. And this can give you some really nice insights into your job. So remember, before I said the default job on Casper will give you 10 gigabytes of memory. This shows that it used 10 gigabytes of memory. That's suspicious to me. I suspect that it actually used more than 10 gigabytes, but then it spilled over into that swap space and ran slower than it would have otherwise. So generally, if you see that the memory amount used is equal to the amount that was requested, then it probably actually used more and went into the swap space. And keep in mind, we don't have swap space on Cheyenne, so that wouldn't be the case there, but on Casper it would. So just a couple of other utilities for me to mention real quick. We maintain on Cheyenne the Q command, and what this does is it runs a non-interactive job, but it still outputs directly to the terminal. So it's sort of a batch job, then we show the logs interactively. And lock the terminal screen until that is run. So you can basically block until something is done. The prototypical case for this would be building a CESM case, because that wants to use an entire node for all of its make threads, make jobs. So it's best run on a compute node, but you still want it to output that on the terminal screen. So it looks like this. You would do q command -a, give the project code, and then -- and then you would have all of your the command and any arguments you want to run. Now, another example is, or another utility we provide is VNC Manager. This command allows you to start a VNC server on a Casper GP100 node, and that allows you to do things like have a remote desktop and do graphically intensive work. Again, here the example would be like running Vapor and doing some rendering of some geophysical data. This can be run either in a batch mode or an interactive mode. If you just run VNC Manager on the command line, it will sort of walk you through the creation of your server. So that's kind of nice if you're starting out. But if you wanted to create a new server just in this sort of batch mode, I could run VNC Manager, create, give the project code, and then give a name to my session if I wanted. Otherwise, it would be called default. And then it'll give you instructions for how to access that remote VNC desktop. So I just want to give some recommendations now for user initialization files. I talked a little bit about these earlier. So jobs will initialize a shell using your .profile file if you're a bash user, or your .tcshrc file if you're a C shell user. This is something we may tweak at some point down the line, but this is how it currently works. So there are some things that you might want to set in these files. You can set default project codes that will, for example, be used by QInteractive, QCommand, and exec Casper. So the PBS account you could set in your files here. And I'm showing bash syntax. Or you could set dav project for exec Casper and VNC Manager, and it would be picked up by those commands. And that way you don't have to specify your project code for every time you run those commands. It's kind of a convenience that you can leverage. Now, a recommendation for the startup files is to not include interactive commands in your init files, as they can block batch job execution. So let's say I have some read in my .profile. That might be fine on the command line, but for a batch job, I don't have the capability to input anything into that read command. So it'll sit there, basically use all the wall time, and the job will never do anything. So that's an easy way to mess up your batch job. And just some general guidance, this is even irrelevant of PBS, but for your initialization files, they're read on both Cheyenne and Casper. So you might want to use if statements to limit the execution of system-specific commands. You could do like if ncar host, something we define for you. If ncar host equals Cheyenne, do this, and if it else, do that. And another recommendation is, in general, to only put commands that are relevant to all of your anticipated workflows in your init files, because they are read for everything. So you don't want to get too specific with those. So that's all we wanted to talk about today. There's some information in terms of getting help. If you go to this website, you can submit, you can get to the place where you want to submit tickets, which is this link down here, actually. But this will show you the consultant on duty if it's not me during working hours. And you can get access to help from the rest of our team. That'll also give you links to our web documentation, so you can see much more detail on the various aspects of how PBS will work. You can also call the help desk phone during working hours. Can't log in right now, unfortunately, because of COVID. And then here's my email if you have specific questions from today, or if you have feedback that you want to give to me personally for things you'd like to see covered, or things that you found useful, or things that you think might need improvement. Always happy to take that feedback. So with that said, we'll wrap this up. Thanks for your attention, and good luck using PBS, and let us know if you have any questions.